Hi, everyone, and welcome back for part one of our series. Following the introduction about discrete time stochastic simulation models. So before we get into the stochastic simulation bit, let's review read frost models in general. So these models have a fixed infectious period duration, meaning that generations of infectious individuals don't overlap. So if an individual is infectious in one time step, in the next time step, they'll be recovered. So in this model, we have P is the probability of infection given exposure. I sub T is the number of infectious individuals or cases at time T. S sub T is the number of susceptible individuals at time T. And then we're going to have these two versions, the deterministic read frost, which the population update is based on the expectation or average, versus the stochastic version of the model, where the population update is based on a binomial draw, which we'll talk more about. And then iterating that procedure of drawing binomials is where the name chain binomials comes from. So getting back to the model, so we also have recovered individuals at time t, that's RT. And now we want to know how we should determine the number of individuals that are in these groups at time t plus 1. So we'll build this up piece by piece. So for each susceptible individual at time t, 1 minus p is the probability of not getting infected by a particular infectious individual. But in order to not get infected, you have to, if you're a susceptible individual, you have to not get infected by any infectious individual. So we have 1 minus p to the IT is the probability of not getting infected by any infectious individual. And then 1 minus that quantity is the probability of getting infected by any infectious individual. So if we let Q equal 1 minus P, we have that the probability of getting infected by any infectious individual is 1 minus Q to the IT. So then we can get our population update. So the number of new infected individuals in the next time step using this probability and the number of current susceptible individuals. So S sub T times 1 minus Q to the IT will be the expected number, and in the deterministic version, the number of cases in the next time unit. So we also then update our other classes. So for the number of susceptible individuals in the next time unit, that they will be composed of the current susceptible individuals minus the individuals that get infected. And then recovered individuals in the next time unit are composed of the current recovered individuals plus the current infectious individuals. Since generations don't overlap, if you're an infectious individual in one time step, you will be recovered in the next time step in this version of the model. So here we have the equations in an order that we're most familiar with from the previous several days. And one thing we can do to check our understanding is think about the basic reproductive number for this model. So if you'll recall, the basic reproductive number is the number of expected number of new infections caused by one infectious individual at or during that individual's infectious period in an otherwise fully susceptible population. It's a little bit of a mouthful. But so we want to know the number of new infections caused by one infectious individual. So if we plug in 1 here, and then if we have N equals S plus I plus R as the total population size, having an otherwise fully susceptible population means that So we have one infectious individual and no recovered individuals at this point. So S equals n minus 1. And that gives us the reproductive number for this model. So here also I've included a simulation of this deterministic system for a reproductive number of 1.5. So that reproductive number is greater than 1. So there is an epidemic. This is the same epidemic that will happen for this initial condition and these parameter values every time, since it is a deterministic model based on the average or expected updates. So, but moving into the direction of having a stochastic version of the model, let's think about incorporating chance, and in particular, recall the binomial distribution. So let's let P be the probability of getting tails on a given flip. Then the probability of getting K tails is N choose K. Oh, I have little labels. So N choose K times the probability of getting K flips all ending tails. So we want to get K tails, but then we need the rest of the flips N minus K to land heads, when that has probability 1 minus P. So this is perhaps a familiar distribution, but we can think of more than just flipping coins. We can also think of probability of a susceptible individual getting infected. And that looks like this. So the probability of the number of new infectious individuals equaling X is the probability of X individuals getting infected by any infectious individual. And then the remaining ST minus X individuals have to not get infected by any infectious individual. So we have Q to IT to the ST minus X. And then we have ST choose X. So there are this binomial coefficient gives us the number of ways that it's possible to choose X individuals out of the susceptible individuals at time T. And then we use the same update for our population. So the number of susceptible individuals in the next time step is the current number of susceptibles minus the number of new infections, and the number of recovered individuals in the next time step is the number of current recovered individuals plus those individuals that are infected, since the generations don't overlap, and one time unit is the infectious period duration. So this is an example of pseudocode that which you may or may not have seen or heard of before, but it's basically just a way of expressing what you're going to code up, but without including all of the details. And this is often helpful to get started. So for the stochastic Reed-Frost model, a summary of the steps for our simulation would be to first define the initial conditions, and then we're going to have this while loop with the condition that the number of infectious individuals is greater than 0 and that the time is less than some pre-specified maximum time, since you probably don't want your simulation to go on forever. So within this loop, if this condition is met, we're going to calculate the number of new infections and then update the state variables SI and R, and then update the time. So it'll be T plus delta T being a day, a year, whichever time unit your system requires. So we can compare the stochastic and deterministic versions of the Reed-Frost model here. So we've seen this one already, the deterministic version, And then over here on the left, there are multiple realizations of the stochastic Reed-Frost model with the same R0. And there's a tutorial for, that will lead you through generating these epidemics, and it's available through the ICI3D R tutorials. So in general, chain binomial models, we can formulate these models to have overlapping generations of cases. So instead of having all infectious individuals recover each time step, we can introduce a probability of recovery at each time step. That is, for any individual who's infectious at time t, their probability of recovery by time t plus delta t is R. So we're going to have probabilities for new infectious individuals and also new recovered individuals, rather than saying that every infectious individual is going to be recovered in the next time step. So we can then describe this update as in terms of random variables, which I won't go into great detail since that could be a course in itself. But X is the number of new infectious individuals and Y is the number of new recovered individuals. So we have these same binomial expressions, but instead of using the probability of getting infected, we're going to use the probability of recovery to see the probability of getting Y new recovered individuals in the next time step. And then we'll use those values that are drawn from this distribution to generate the values of our system at the next time step after delta t amount of time has passed. So we've been talking in terms of probabilities P and R, but it's important to know that these probabilities can be thought of in terms of the parameters that you've seen for the differential equation models. So for those models, some of the simple models have an instantaneous hazard of infection for an individual susceptible individual of beta I over n. And then we can define this probability of infection by time t for a susceptible individual using this hazard of infection for any susceptible individual, and then multiplying that by the duration of time. And we have 1 minus e to the negative beta I over n delta t. And so this has to do with waiting time distributions. And we will discuss that a bit more in the next session. But similarly, for the recovery probability R that we introduced, we can define that as 1 minus e to the negative gamma delta t, where gamma is the recovery rate parameter that has shown up in the other models. So again, we have another set of pseudocode for the chain binomial simulation. So it looks very similar. First, always define initial conditions, and then we have a loop while the number of infectious individuals is positive and the time is less than the specified amount of time you're willing to wait for your simulation to end. We're going to calculate the transition probabilities, determine the number of transitions for each type, update those state variables, Si and R, and then update the time, which will be plus delta t, a fixed amount of time. So that's the end of part 1. Thanks for joining, and I'll see you soon for the next part of the session. Thanks.